Hello, good afternoon. So this is lecture number 12. On Wednesday, we discussed some very important kind of philosophic ideas in mathematics. That is, when you need to overcome a new, more difficult problem where your current tool cannot help, a very helpful approach is to generalize what you currently have. Make your tool more general, broaden its scope so that you have new tool that can help you solve the new problem. But very importantly, at the same time, your new tool cannot break the old tool. In other words, the new tool must work fully with the existing old tools. 100% compatible. Otherwise, you are not just generalizing or broadening your tool. You are inventing a totally different tool. So, in other words, the old tool becomes a specific or special case of the more general new tool. This is kind of idea that will be used again and again in mathematics. In many more advanced mathematical branches, you will see generally this idea. So we just got the first taste of this idea by overcoming the fundamental problem. When we do subtraction over natural numbers, we cannot subtract a large number from a smaller number. And the way to do that is to broaden our definition of numbers. And we naturally extending our natural numbers into the left-hand side of 0 on the number line and define some negative integers. And let's quickly review what we did last time. So we were motivated to solve the problem by first extending the decrement operation, which, as we discussed earlier, which is the inverse operation of increment. But both increment and decrement with the little case, they only apply to natural numbers, and that's by definition. And in particular, the decrement operation cannot go beyond 0. So we want to expand that definition. So we redefine a new decrement operation. And it overlaps with the old one because on all natural numbers, the two are exactly the same. In other words, capital D decrement is the same as the little case decrement for all natural numbers except 0. We cannot decrement with the little case, cannot do decrement on 0 because that's not defined. So we first redefine decrement so that for any positive integers 1, 2, 3, 4, the two operations are exactly the same. Then from that point on, we define, it's very important to understand this is just a mere definition. We define this capital D decrement can operate on 0 and on a new group of numbers, which we call negative numbers. And the way the negative numbers are defined are very similar to how we actually defined natural numbers in the first place. So we use this capital D decrement operation on 0, then recursively generate more numbers. And we call those numbers negative numbers. And the specific way of doing that is just like this. We decrement from 0, get a new number, and we call that negative 1. And from negative 1, we further decrement, get negative 2, and so on. And we can do this indefinitely. Therefore, this is kind of just similar to how we define natural numbers or positive integers. So you must understand this kind of similarity right there. They are all just definitions. But the gist here is that this decrement, capital decrement, is a common operation on all integers, whether it's a positive integer or negative integers. Why? Because we already said that for positive integers, this capital D is the same as little case decrement, which is a common operation because decrement is just the inverse of the increment. And we know increment little I, that's a common operation across all natural numbers. Therefore, because of this chain down reasoning, the decrement, capital D decrement operation is the same for all positive integers. But now we further extend this to define it to continuously use this common operation first on 0, then generate a -1, then on -1, then generate -2, and so on. So it's important to understand this capital D decrement is a common operation of all integers. Okay, so it looks just like this. In the bottom, we have this decrement. You can go from positive integers to 0, then further into negative integers. And on the number line, because we are effectively using the same decrement operation, it's easy to understand that the distance between any two adjacent negative integers is again just the unit length, which must be the same as the distance between 0 and 1, which we call unit length. We'll see why this is important later today. So with this way, we have defined all integers. We already have natural numbers, which is 0 and 1, 2, 3, 4, which we will call positive integers. Now we get a -1, -2, we call them negative integers. So all the three types of integers, negative integers, 0 is unique all by its own. It's neither positive nor negative. So negative, 0 plus positive. Together we call them integers. Okay. So with this decrement operation, now we were able to define, actually generalize our subtraction a little bit further, but not completely what we needed. What did we generalize? Now we subtract a number from another number. The number being subtracted from doesn't have to be natural numbers. It can be any integers. But the number being subtracted, for now, it's still an integer. Because that's how we define subtraction continuously, right? You can just do decrement, now you can go across 0. So subtracting a natural number is simply repeatedly doing the capital D decrement operation. That's how we were able to define this. As I mentioned last time, this particular, just I think that was a typo in the previous slide. I didn't have time in just fix it in time, but this is the correct version, okay? So this is subtraction of natural numbers from an integer. It's important to understand this is different from our earlier subtraction definition, which only applies to subtracting a smaller natural number or equal natural number from another natural number. Now the difference is that we can subtract a natural number from any integers. It doesn't have to be another natural number. And the way to define that is starting with this integer, which m could be negative. We just repeatedly perform this capital D decrement operation, which is very similar to how we define it. But the difference is now we are using the capital D, so the new decrement operation can go across 0 to the left-hand side of 0 on the number line. All right. So this is still, be mindful that this is still not what we wanted. We want the subtraction between any two integers. No limitation. Okay. So for now, there's still a limitation, but it will help us go to the next step. So for now, bear with me. We already generalize or expand our subtraction definition somehow. This is a significant just an improvement, but still not 100%. Similarly, now we can define the inverse of the capital D decrement, which is just capital I increment. And the definition is very straightforward because now the capital D decrement applies to all integers, positive, zero, negative, wherever you go on the number line. As long as you have an integer, the capital D decrement works. Now the inverse of this capital decrement is just the capital I increment. So now the definition is again similar to how we define the little d decrement in the first place. We assume we have an integer m because now m minus 1, which is just capital D decrement, is well defined. It doesn't matter whether m is positive or negative, m minus 1, just capital D decrement, is always well defined. Therefore, we know that's another integer. So we can define this capital I increment on this m minus 1, which is 1 less than m, effectively. We define this back to m. And it's very easy to see this capital I increment will be fully compatible with the little I increment we began with. That's everything started. Remember how we define natural numbers? We need that little I increment, but that's only for the right-hand side of 0 for the natural numbers. With this new generalized definition of increment, it's easy to see this is fully compatible with the little I increment we already had. Okay, with this, now we are ready to define addition of a natural number to any integer, not just to another natural number. Why? Because now the increment, capital I increment, is well defined for all integers, not just limited to natural numbers. Therefore, whenever we need to add some natural numbers, doesn't matter where you begin on the number line. It could be on the right-hand side of 0, could be 0 itself, or could be a negative number. That's the beauty of this more generalized definition of addition. Now the addition is allowed to begin with a negative number, then add some natural numbers. So the definition here is very similar to what we had earlier for the little I increment and the addition of natural numbers. The major difference is that we begin with any integer, and we use the capital I increment operation. Other than that, everything is very similar. So this is what we covered last time. It's very important to understand why we are doing this, why we took so much pain to expand into this. Because mathematics is all about the rigor. We have to understand whenever you see something, the formula, whatever, you need to understand why it works. It's either proven or via some definition. It cannot come from nowhere. Just because your teacher tells you this is true, you memorize it. Yes, you memorize it, but you don't understand why. That's really poor. Okay, so now there's a very important inverse relation between this capital decrement and increment. We begin with the natural numbers. When we have natural number, we begin with increment, right? Then the little d decrement. But there's a constraint. Little decrement cannot be on 0. So the smallest number it can work on is 1. Therefore, we have those two relationships, which is very obvious. If you increment a natural number, then decrement the result, you will go back to where you began with, right? You first do increment, then on top of that do a decrement, it will be back to that very number. This is obvious and can be easily proven. On the other hand, if you reverse this order, almost the same, but if we do decrement first, then do increment, we have to be careful. M cannot be 0 because decrement on 0 is now well defined. So if you reverse this relationship, almost there, but there's a constraint. M cannot be 0. Otherwise, this doesn't make sense. It's not well defined. That's what we have with the little case increment decrement, this inverse relationship. Now, after we expand our numbers into all integers and generalize the increment decrement to capital I, capital D increment decrement, we are not limited by this otherwise m not equal to 0 constraint. So we have a free version like this. M any integer. If you do increment first, then decrement second, or you do decrement first, increment second, you get exactly the same number you begin with. And that's very obvious. And of course, we can formalize this, prove this, but this is so obvious. So this is very fundamental, okay? So essentially, you plus 1 and minus 1, or you minus 1 plus 1, all gives you the same original number. Okay? So we will see how this will help us later today. Okay. So our generalization of the addition and subtraction operations for integers have not been complete yet, right? Because as we mentioned, this is what we can do now. The first number can be any integer, positive, negative 8, positive, doesn't matter. But the second number, whether you are adding or subtracting, cannot be negative. So in this case, we are subtracting negative a plus 5, that's negative 3. Negative a plus 15, that's 7. A subtracting 13, that's negative 5. Negative 8 subtracting 13, that's negative 21. By the way, how do we know those results? Think about it. The only way to know those results is go through the definition. What is definition? What is negative a plus 5? You start with negative a. You count rightward or making right facing jump 5 times. On the number line, you can clearly see that's negative 3. And the same for the other 3. So everything for now is through definition. Okay, essentially, that's how it works. But we have something that we cannot do at this time, and that is something like this. If we add a negative number, negative integer, actually, a plus negative 5, what does it mean? Well, negative a plus negative 5, what does it mean? Well, a subtracting a negative 5, or negative a subtracting a negative 5. What do those expressions mean? They don't mean anything because we have not defined what they mean yet. All right? Remember, mathematics is about rigor. We cannot write things just because we roughly feel it makes sense and it works in the real world. But if you have not given a thing a proper definition, you just cannot use it. And for now, we have not defined what those red expressions mean. And that's what we're going to do today. Okay. So, first, we want to clarify some very important things about this quote-unquote subtraction operator or symbol. Because when we introduce the negative integers, it seems that we use it, right? -5, we put that same symbol in front of all the positive integers to get the negative integers. We did not even mention what that means. Well, that thing, we call it a negative sign. But is a negative sign the same thing as subtraction symbol? Yes and no. Yes part, they look exactly the same. The no part, they're actually very different. So that's exactly why studying negative numbers and arithmetic about negative numbers, addition, subtraction with negative numbers can cause great confusion and generate tremendous difficulty. Don't worry, we'll get everything straight today. That's the good news. Okay, so first we need to clarify this symbol. Let's just call this is just symbol, what it means. In mathematics, very unfortunately, this symbol is very confusing in mathematical notations for beginners. And even for many adults, they cannot really explain what it is. That's the reality in America, unfortunately. So what this symbol means in mathematics? Well, we have so far learned two meanings for this symbol. Okay, very important stuff. First, this symbol represents subtraction operation, right? So far, we only properly define subtracting a smaller or equal natural number from another larger or equal natural number, or subtracting a natural number from any integer. But regardless, we have used this symbol as a subtraction operator. And this subtraction operator, it requires two operand. So two operands, for example, a minus 5, or a subtracts 5, a subtracts 13, we need two numbers. We need two operands for this one. It's very important to understand subtraction is an operation that needs two, not just one, two operands. Okay? There's some very weird name for the first number and second number, but that's not what we're going to discuss today. Don't want to confuse you with too many just jargons or weird terms. But we understand subtraction is an operation. It's an arithmetic operation that requires two guys to work with. On the other hand, when we say -1, -5, and so on, what is that? Well, we call it a negative sign. But really, a negative sign, what is it? What do you mean by put that little dash or subtraction symbol, whatever you call it, in front of another integer or positive integer? So when we have -5, we put this symbol in front of 5. This negative sign is actually a single operand operator. It's very important to understand what we are doing here, meaning take negation on a number. So -5 really means the negation of 5. But what is the negation of 5? We'll talk about that later today. But for now, you should break any misconception you may have when you look at a negative number 5. Yes, we call it a negative sign. But what is sign? It's sign just a symbol, right? So this is just a sign. If we don't give it any meaning, it's nothing but just a symbol there. We could choose a different symbol for this negative sign. It just means something. But what exactly is that? And then we will see why we can expand this so-called negative sign into a negative negation, actually negation operator. And this operator only takes one operand. So it's a single operand operator. That's very different from subtracting. It only works with one guy. And this operation we call negation. Okay, so in fact, this is just a side note. There's also a single operand plus a positive operator, just kind of symmetrical with the negative sign or negation operator. This just means that take the positive on a number. But if you apply this operator on a number, it doesn't get you anything. The result is still the same number. That's why we usually do not use this operator unless we want to emphasize certain things. In some cases, usually we don't use this single operand operator, positive operator at all, because it does not give you any actual things. It just means if you apply this positive operator on a number, it still gets exactly the same number. Okay, it may sound like a dummy operator does not have any effect, but in some cases we do want to emphasize what it does. It just takes positive. Okay, that's actually not very relevant to what we will study today, but just for some curious minds, you may want to know this. Now, let's talk about this negation operator. Let's pause for a second. Once again, this is very different from subtraction. This is a single operand operator. Let's carefully review how we define natural numbers and integers shoulder by shoulder. How did we define natural number? We start with 0, which is based on the axiom 0 is a natural number. We use this little I increment, which now we know for natural numbers is the same thing as the big I, the capital I increment. So 0 to 1, 1 to 2, to 3, to 4, doing that recursively. How do we define integers? All we need is just to define negative integers, because 0 and the positive integers are already there. They're just natural numbers. So how do we define negative integers? Once again, we start at 0. We decrement, decrement, decrement to get a -1, -2, -3. And we deliberately reuse the same set of symbols that represent natural numbers, 1, 2, 3, 4. We merely prepend this negative sign for each one of them. So with how we use the notation for negative numbers, it's very clear to see if we have a positive integer 5 and a negative 5, which we deliberately pairs up with 5, right? We just add a sign, this negative sign, in front of 5 to denote -5. So the two must have a lot of things in common. That's how we deliberate this. And an important property is that because how we define those negative integers, you can see both 5 and the -5 are equally distant from 0. That's because of the definition. -5 is decremented from 0 5 times. And the 5 increment from 0 again 5 times. And each time the increment, they involve a pair of inverse operation. Therefore, 5 and -5 are equally distant from number 0 on the number line. 5 is to the right of 0, negative 5 is to the left of 0. So this is very important, equally distance from this number or point 0 on the number line. And this property does not just apply to 5, right? It applies to any natural numbers m. So when we write down a negative number in the format of a negative m, negative m, where m is just a natural number, not 0, natural number, then what we mean by this symbol, a negative sign, and this positive integer m, we really mean it's just what we would have to decrement from 0 m times. Agree? So, therefore, motivated by this, we want to now give this negative sign, which is nothing but just a symbol to help us to just make notation on those negative numbers. Now we want to give it some more specific meaning. We want to say this negative sign is actually an operator that operates on the positive integer to generate the corresponding negative integer. Does that make sense? Now we want to say this negative sign is an operator on 5, and the result is negative 5. And we actually want to take one step further. This operator, we not only wanted to work on a positive integer 5, but we also want it to work on the negative integers as well. Now we just need to properly define what this operator is. So motivated by the fact that 5 and negative 5, they're just on the right-hand side and the left-hand side about 0, symmetrical on the number line. Just 0 is the kind of mirror. They are mirror images of each other, motivated by this fact. By the way, not just 5, like we mentioned, for any natural number m. Motivated by all what we just observed, we want to define this negation operator in a way. If m is a positive integer like 5, so in this equation or expression on the left-hand side is this operator, which we call negation operator on 5. And the result is negative 5 without the parentheses. That's how we write it down. So it's important to understand what this expression means. On the left-hand side, we have an operator on a positive integer. And the result is a negative integer we normally write in this format, where on the right-hand side, it's just a combination of this symbol and the positive integer m. That's why now we say the negative sign is actually an operator, because those two mean the same thing by definition. Okay? On the other hand, we also want to have this. What does this mean? Well, remember, for now, m is still a positive integer, right? After using this negation sign, we get a negative integer. Remember, this negative 5 inside this second parenthesis in this second expression is what we have on the right-hand side in the first expression. So we are trying to use this operator again, but this time the operand is a negative integer, negative m, which itself is the negation of m. So now we define the negation of the negative m is just m. Remember, this is not magic. This is just a definition. In other words, if you have a number on the right-hand side of 0, its negation is corresponding mirror image on the left hand of 0. But on the other hand, if we take the left-hand side number as the input to this operator, which is what we have inside the second parenthesis, we define this operation to get us back to the original number on the right-hand side. So the two go shoulder by shoulder. It's not something that's brilliantly proven or something. This is just the definition, which actually makes sense because it's just a mirror image of each other. So this negation, you just think about it like a mirror back. And that's exactly why we can define this way. So, in summary, it doesn't matter where you begin with. You can begin with a positive integer or negative integer. Whenever you take this negation operator, you get the other side mirror image about the 0. Okay? So, also here we say that work on any positive integers, but because of the second definition, this negation operator can effectively work on any integers, positive or negative. How about 0? 0 is always back to itself, 0. There's no mirror image, right? Because 0 itself is not a mirror. So negative 0 is just 0. Negative 0, 0 again, always 0. So it doesn't matter you put how many negation operator, how many layers you put in front of 0, it's always 0. On the other hand, you put many layers of this negation operator in front of a number, then the result will fluctuate between 5, negative 5, 5, negative 5, and for many times, depending on how many layers of this negation operator you put there. So now it's clear what's the difference between a subtraction operator and a negation operator. So it's important to understand that all this symbol above, meaning in those two expressions, they are all the negation operator. Even in the first one on the right-hand side, when we write down a number like negative 5, we call that a negative sign, but it's actually this negation operator on the positive integer 5. Now don't ever get confused. What is negative 8? It's a negation of 8. Okay? Even when we write negative 8, put that negative sign is the negation operator. Okay? And we call 0 is the origin point, or simply just orange of the number line. Okay, so now we have some exciting stuff to do. First, we just review what we just said, right? Increment, decrement, decrement, increment. As long as you put 2 back to back, it doesn't change a damn thing. It's still that original number. You get the exactly same number. And importantly, this number is not limited to say, cannot go beyond 3rd point. It can be any integer on the number line, no matter where you start. On the right-hand side, left-hand, it doesn't matter. As long as you are doing increment, decrement, one and the other paired together in each order, decrement first, increment first, doesn't matter. As long as you do the 2, they flip back to the same original input number. Okay, this is what we just see. Why this is important? Because this will give us 2 seemingly trivial but very important property that will allow us to complete our definition of addition and subtraction on integers. So the first theorem is something like this. you have a number n, which is an integer, where n is any positive integer. For now, this is required. If you do this, n plus, because n is a positive integer, so if you take a decrement on n, it can be at least 0, right? It cannot be negative. So decrement n is always non-negative, cannot be non-negative. Therefore, the left-hand side for now is well defined. We have already defined what that means. n plus any integer that is not negative is well defined. So because n is a positive integer, the decrement of n cannot be negative, and the left-hand side of the equation is well defined. What is the result? This theorem says that the left-hand side is just n plus n, then take decrement. In other words, the decrement can go first into the second operand, the number being added to the first number. You can do decrement there, or you can postpone the decrement operation. You first perform just n plus n, which of course is also well defined. Then take the decrement on the sum. This theorem says that it doesn't matter whether you do first decrement on the second number being added, or you do decrement on the total. The two will give you exactly the same thing. Why this is true? Well, intuitively, you can see this is very easy to understand, right? For example, let's just say 6 is the n here. Okay, let's just say m equal to 8. So if we do m plus decrement of n, so we are doing a plus decrement of 6, and that is just a plus 5. This theorem says that a plus 5 equals to decrement of a plus 6. Of course, this must be true. So it's very easy to see why this works, but this is not a proof. So what is a proof? Proof in mathematics is that you need to have a very rigorous reasoning, a chain of reasoning. Every step of the way, you either use some definition or some already proven fact we call theorem. In fact, we are trying to prove a theorem right now in the first place. So how do we prove this? Well, we write down a proof. It's very important for you to get some exposure to what proofs are and how to write them rigorously. So what do we need to prove? We need to prove this equation, right? m plus decrement n equals to decrement plus m, decrement of m plus n. So how do we do it? Well, while this is not a proof, it gives us some insight into the nature of the problem. That's why also you cannot use specific examples to as a replacement for proof. They can give you great ideas. You cannot just say what inside the green box is the proof. No, that's just a proof of one example. But you need to prove this for any number. You cannot prove for all of them, right? You cannot say n is 6, m is 7, they all work, therefore there's infinite many numbers. You just cannot do that. So how do we write a proof? Well, based on this observation, we have an idea how the proof should be carried out. So we first write this because it involves m plus 6. So instead of m plus the decrement of m, we do m plus n. Because now what? n is one more than its own decrement, right? So, based on what we have here, look, increment, decrement back to that number, we can easily write this as m plus increment of decrement of m, right? Another parenthesis. We are not changing anything. We just use the fact that we already proven that n is just first take decrement on itself, then take increment on that result to get back to that. So n plus n just equals to this one. And this, why this is true? We already proven that right here. Decrement, increment, do that twice, get back to yourself. Okay, now what? Remember how we define addition? Addition, because now n is a positive integer, we know this is same thing. This is doing this, n plus 1. So this is n plus what goes inside of this. We do this first, n plus 1, right? What is this step? This is just our definition of what is addition. Remember, addition just repeated adding 1 or increment, add 1, add 1, add 1. So if we do this first, then if the number being added is 1 bigger than this guy, by definition, the very definition of this expression is this. That's just the definition of the addition. We want to add a number that is 1 larger than another number, and that definition is true that earlier addition just add 1 more. So this is nothing but increment of decrement of n plus decrement n. Now think about this very carefully. It looks like we are wasting our time doing a lot of obvious things, but every step of the way we are using a rigorous step to show a chain of equivalence relationship, and we start with this m plus m and arrive at this expression. Now what? This is actually just 1 step away from what we need to prove. We want to prove this relationship, right? But remember, we can use decrement, increment on the same number, or we can do this at the same time. So we just prove m plus m equals to increment of m plus decrement n. Now we use decrement on both sides. In other words, now we decrement m plus n, which is on the left-hand side of this established equivalence. This must be the same as decrement of this whole thing right here, right? Because what go inside the decrement operator are 2 identical things. Therefore, if we take decrement on both, the result must be the same. By the way, that's another axiom we don't need to discuss. That's the axiom about the very meaning of equation sign, which is equal sign. So, but what is this thing inside this? It's just increment of this thing. Now, on top of that, we do another decrement. So the two cancel out each other. So the right-hand side is just this guy. Does that make sense? Now we are doing increment and then decrement. Therefore, this is nothing but n plus decrement of n. Looks like I'm ridiculously insane doing all those to just manipulating all those algebraic relationships, but that's exactly what math is about. We are not doing nothing. We are doing something really significant. We just arrived at this relationship. And look, what is this? This is exactly what we want to prove. We just swap the left-hand side with the right-hand side. On the right-hand side, in our result, is m plus decrement n equals the left-hand side, which is decrement of n plus n. And that is exactly what we have. We want to prove in right-hand side. Magic? Yes? No. This is what a proof is about. So, you think this is simple to understand, but give it a mathematical proof does take some effort. The importance is, in this proof, every step of the way, we are not merely making an argument, try to convince someone without evidence. We need solid reasoning every step of the way. We need to show why that step is true. Let's just review what we just did. So n plus n equals to this guy, because we have already shown that if you do decrement and increment on n, you go back to n. That's the same thing. Therefore, this is true. And from here to here, why this is true? This is just the very definition of addition. When you add a natural number, add 5, add 6, add 7, just repeatedly adding 1. So add 7 is really you first add 6, then add 7, right? So therefore, from here to here, you do inside first, and then add 1 more. That's just definition of addition. And now we know this is just increment of this whole thing. So we go from n plus n, get here. Then we simultaneously perform a decrement operation on both sides, and this get what we want in the original right-hand side. It's decrement n plus n, and here we once again use the earlier result. If you do increment here, then perform decrement, it goes back to the original, which is exactly what we needed in this theorem. Okay, what it says theorems. What is the other one? Similarly, this is a little bit harder to understand, but the proof will go through exactly the process. And because we are running out of time, we won't prove it, but you can read the handout, which is kind of overdue now. But you need to understand this. When we subtract a decrement of n, we are effectively first subtract that n, then do an increment. Let's think about what this is. What this means, m subtracting a decrement of n, and this equals to we subtract n itself without performing the decrement first. We subtracting n. But at the end, we do an increment. That's very important. Why this is true? Well, you think about it. If we say a subtracting 5, that's what here. That's left-hand side. But because we're subtracting the decrement of another number, so 5 must be the decrement of 6, right? 5 is decrement of 6. 6 is one larger than 5. But if we ignore the decrement operator, we directly subtracting 6 first. What happened? We subtract a number that is 1 larger than the number we want to subtract. We do the decrement operations 1 extra time. Because originally we just need to decrement 5 times, we're subtracting 5. But now without doing this decrement operation before we do the subtraction, we ignore that. As the result, we're subtracting 6. We'll do decrement 6 times. Therefore, if we temporarily throw this decrement operator away, then we will effectively doing 1 extra decrement than we should. So to compensate this actual unnecessary decrement, we have to do 1 increment on A subtract 6 to cancel this actual decrement. And that's the reason why this is a theorem. And the proof will, just like what we did earlier, you will see that how it works in the handout. But for now, you can intuitively understand why this is true, but this is not a proof, just like in the previous example. Therefore, we have those 2 important theorems. So the first one is easier to understand. The second one is a little bit more complicated because in the sense we flip the side, but that's huge. Okay? But both can be proven. Why this is important, those 2 theorems? They gave us insight on how to properly define adding or subtracting a negative integer. That's coming up next. Okay, before we look at this definition, let's consider the following problem. Let's consider adding numbers. 8 plus 7, we get what? Count forward 7 times from A, and we know that is 15. But if we do 8 plus 6, we are doing 1 less than 7, right? What do we have? It's 14. Why is 14? You have to think of this in the reverse way. If we do 8 plus 6, let's just say we don't know what is 14. We just know this is some number. But if when we do 8 plus 7, that number must be 1 more than this, right? Because we are adding 1 more. Whatever the result there must be this result plus 1. Therefore, the number being added is a decrement, then the result will be correspondingly a decrement. 14 is just decrement of 15, right? If we move this a little bit further, so 14 is decrement of 15. So when we A plus 7 equal to 15, then A plus 6 must be 14 because the number being added is 1 less, the result will be 1 less. That's easily understandable from the very definition of what addition is all about. It's continuously counting forward when we add a positive integer. So we can continue this and until we hit A plus 1 equals to 9 and 1 less, A plus 0. Of course, we know this is defined to be A itself. Nothing happens. You are not doing anything. With this observation, you can see that when you decrement the number that is being added, the result will also correspondingly decrease and decrement. And this is so far what we have for addition. We cannot do anything further. Remember, this is all we have. Of course, the first number doesn't even need to be a positive integer. For example, we can start with -1, but all the numbers will be 16 smaller because 8 and -8 they differ by 16. But that's not the point. The point now is that based on this observation, what do you think? What should we have if we define this guy? A plus -1. Remember, we don't even have a definition of what this animal is. We have no idea this what should be. But based on what we observe, what do you think what this should be? This should be continue the trend on the right-hand side, one less, right? This should be decrement of the last result, which is a plus 0 equals to 8. Because now we are adding just 1 less than 0. And we don't know what that means. But what we wanted it to be, in order to be consistent with everything we have so far, if we want to define this something, we can define it to be anything. We can define a plus -1 to be 200 because this is just definition. We don't have anything. Well, we can define this to be -99. But if that's the case, if we put 200 or -99 here, did you see what goes wrong? This result does not follow the original trend. When you add 1 less, the result should be also go just down by 1 less. This would completely destroy what we have already, and that trend cannot continue. But on the right-hand side, it's a discontinuity, but on the left-hand side, you will just keep doing 1 less. So this does not make sense. The only sensible way to define a plus -1 is to define this way. Make it 1 less than the last result you get, which is 8. So therefore, this as a definition just follows what we should do in order not to break anything, so that we can continue what we have already have. In other words, if we define adding a negative number this way, this will be consistent with what we already have for adding a positive integer. And that's exactly what we are going to do for this definition. Okay? So, definition, addition of a negative integer. Now, it's not a natural number anymore. It's not a 0. It's not a positive integer. It's a negative integer to an integer, any integer. So what is this definition? Okay, let m be any integer and n be any positive integer. Why positive? You will see that because we'll take a negation. Okay, so because n is a positive integer, then addition operation, this addition operation over m, and very carefully, the addition operation now is on negative n, which is the negation of a positive integer n. We know that this is a negative n because this is a negated version of n. So now this operation m plus, we use parentheses to make that clear, we are adding negative n, not n, negative n to m. And what is it? We just define it. -1, oh, I'm sorry. Subtracting 1, subtracting 1, subtracting 1, n times from m. Why this definition? That's exactly where we got here. If we continue this, what is m plus -2? It must be further decrement from decrement of a. Right? And this will continue, and put in to that way, this is really, we should define this as subtracting 1, subtracting 1, subtracting 1, subtracting 1. Remember? Because now, all this is well defined, we can subtract a negative number, a positive number, just decrement, right? This is just decrement. Remember, decrement is always well defined. So this is really what we want if we want to continue this. Therefore, when we add a negative integer n, negative n, to an existing integer m, we just want to do n times of the decrement, capital D, because only that makes sense, well defined. We just want to decrement n times from the first number, which is being added to. Does that make sense? So now you understand why m plus negative n is actually m minus n. We will see that shortly. But for now, this is just definition, okay? This is not magic. This doesn't have to be proven. This is nothing but definition. But this definition gives us a nice continuity from what we have already defined. That is addition of a natural number. Now with this addition of a negative integer, the two, because of this continuity, the two can be unified. There's no abrupt jump or just kind of change. The whole thing is seamlessly smooth. It's consistent. It's coherent. So m plus negative n is defined as m decrement by 1, or we call it subtracting 1, subtracting 1, subtracting 1, all the way. So adding a negative number is effectively doing decrement by certain number times, and number is the original negated version. Unnegated version. Okay, I'm sorry. Unnegated version. So this is the definition of adding a negative integer to an integer. Similarly, if we do subtraction of a negative integer, what is m subtracting negative n? Well, this is kind of a mirror image of what you just did because of this second theorem. Remember, if you do subtracting decrement, you actually postponing that decrement, but convert that to increment. So m subtract the decrement of n equals to you just m subtract n, then do increment. Based on that, you will see why this makes sense. If you subtracting a negative integer n, subtracting a negative integer negative n, you are effectively doing increment n times, and that's given that a new just once again, if we start with 5, if we subtract 5 from a, that's 3, right? If we decrement this number by being subtracted, what is a subtracted 4? Well, it goes up. The number being subtracted is 1 less, but the result is 1 more. This can be proven. And if we continue, so the number being subtracted reduced, the result goes up for the reason we already explained. Because now you just take 1 less decrement. Of course, the result will be actually an increment. So if we continue this, when we reach 0, that's just 8. But you can see that the right-hand side keep going. So if we want to a subtract negative 1, what do you think? It should be 9. That is a plus 1, or increment on a. And you keep doing this, this will be a plus 1 plus 1. This really is the motivation for us, once again, to keep the continuity. Don't have something that will break what has been working. So if we do this, you will see that m subtracting negative n would be m plus 1 plus 1 plus 1. How many times? N is a positive integer, it's a natural number, just n. And once again, this is just a definition, all right? This is perhaps the single most confusing point when new students, young students, learning negative integers and arithmetic about negative integer. You subtracting a negative number, you get a lot of positive things. You get one, get one, get one. Actually, as the result of those two definitions, we will easily see something surprise. What is that? Compare our earlier definition of subtraction of a natural number from an integer. What was that definition? So m minus 1 is decrement. We all know that. That's how we define minus 1 or subtracting 1. M subtracting a positive integer n times, that just keep decrement, right? That's subtraction, how we define it. Until something, this can certainly go across the 0. All we need is to guarantee that n is not negative at that time. We don't care about n. N cannot be negative. As long as it's not negative, we are fine. But the very definition, of course, obviously is just decrement, decrement, decrement many times. Look at what we have now. Well, the title is different, but the actual definition portion, they look exactly the same thing. In the previous one, we have decrement, decrement from m. Here, once again, we have the same thing. So that means that the two left-hand side must be the same. And this can be written in a rigorous way, and that will be done in the handout. And with all cases, not just n is a positive integer, this can actually be any integer. That's a further extension. But what we have is that the two left-hand side in those two definitions must be actually the same. So, in other words, m, any integer, plus a negative n, where for now, n is positive integer, but it's very easy to prove for the negative integer because that decrement-increment relationship, this is still true. So generally what we have is that m plus negative n equals to m subtracting n. Very important. So this is one of the easier results to understand. The next one, it's the same idea, same philosophy, but a little bit less obvious, and it's a little more counterintuitive, and that is if you're subtracting a negative number from number, you're adding the positive version of that number or the negation of that negative number back to the original first number. So m subtracting negative m equals to m plus n. And the reason to understand is that you compare those two definitions. The first one is from last lecture, when we add a natural number to another number. Of course, that's just continuing adding one. But for today, we just saw that when we subtracting a negative integer, it's always defined exactly the same way. That's today's definition. The two definitions right-hand side are exactly the same. Therefore, it can be easily shown, not easily, it takes some effort, but it can be shown m plus n equals to m minus negative n. And you have by now, you have a solid understanding of a counting process. From counting, which originally is increment, we introduce the inverse, which is decrement, so that effectively we have two-way counting. We can count up, you can count it down. Also, in count down, it will be negative. But the idea is the same. So with that, now we can understand why this super confusing, super important relationship is true. M subtracting a negative or negative version of n equals to m plus n. That's it for today. I know now we are getting quite abstract, but we took pain and effort to give you a really deep understanding of why those things work in arithmetic and correspondingly in algebra. Okay? Because without truly understanding why those things work, you will be reduced to a robot just to memorize this formula without appreciating why it actually works. And that's for today. Thank you. You will get, I'm still working on them. As you know, this is the first year. I have been very overwhelmed. You will get some homework and the handout. I will see you next week. Bye.